Welcome to the first section of CUDA Masterclass course. We will start this section by exploring some of the background terminology associated with the parallel programming in general. This diagram shows you a basic computer architecture diagram of von Neumann architecture, which more or less any of our modern day computers are based on. In any computer program, instructions are stored in persistent memory or hard drive as executable file. When we run it, the instruction for the program will be loaded to CPU and basic data is going to load it to the RAM. And computing unit or the processor of our computer will start executing instruction while taking inputs at runtime, and program will output the relevant results based on those inputs. No matter how complex our application or program, still this is what is going to happen. Notice, according to this model, we are executing instruction one after another. But in modern day computers, we can run multiple applications at once. For example, if I open up my Task Manager window, you can see multiple applications like Visual Studio, multiple instances of Google Chrome browser, Microsoft Word kind of applications running in my PC at the same time. So how does my PC is able to execute instruction from multiple applications at once? To understand how even a single core processor performs this kind of simultaneous executions, we have to get to know the concept called process first. A process is an instance of computer application. When we run an application, instruction for that application will be fetched to the processor. Also, memory will be allocated in RAM to hold runtime resources. This running instance refers to as a process. Other than the memory and image of executable code or the instructions, there is an important thing called context is also associated with the process. Context is referring to a collection of data about process which allow the processor to suspend or hold the execution of a process and restart the execution later. Memory addresses, program counter states are some of the data contained in the context. When running a multiple applications or process simultaneously, if we have only single core processor, that processor will execute instruction of these process in round-robin fashion. Time slot will be allocated for each process depending on the readiness of particular process memory and the priority of that process. So if we arrange the execution of the instruction in a processor in timeline, one possible outcome would be look like this. Here I have colored each time slot with same process color which is executing at that time slot. So according to this convention, processor execute instruction belong to process 1 in first two time slots. Then in the next time slot, it executes the instructions belong to second process and so on. This type of execution is possible due to the mechanism called context switching. With context switching mechanism, processor can load context of a process and execute it from the state it hold the execution previously, and then it can suspend the execution of that process and switch the context to another process to start the execution of that particular process. We call this type of execution as round-robin fashion execution of instructions. Another important concept which is very similar to process is a thread. Thread or thread of execution is the smallest sequence of programmed instruction that can be managed independently. Thread is component of a process. Every process has at least one thread called main thread, which is the entry point for that process. You can assume thread as a scaled down version of a process. One major distinction between threads and process is that within the same process, multiple threads can coexist and share the memory between them, which of course the memory allocated for that particular process. But if we consider two processes, there will not be any sharing of resources between them. Okay, our main goal in this course is to learn parallel programming with CUDA. Even in modern CPUs, there are multiple cores available, which means multiple threads or multiple processes can execute simultaneously without context switching. This type of simultaneous processing of multiple threads is referred to as parallel processing. Let's first understand the parallel processing or parallel computing with a real-world example. Imagine you are going to build a house. Here, I have listed some of the subtasks that we must finish in this process. We have to first make a plan for the house and then we should lay the foundation. Then there will be tasks like bricklaying, plumbing, roofing, painting, furnishing, and many other subtasks as well. Now let's arrange these tasks in a timeline now. Some of the tasks like planning and foundation laying may need to perform sequential order or one after another. But other tasks like bricklaying, plumbing, wiring, and sewer pipe laying can be done simultaneously. For example, if our house has multiple rooms, some workers can work on plumbing some part of the house while others can work in bricklaying in another part of the house and so on. Ultimately, the idea is that in almost every process, there are some parts which should perform sequentially and there are some parts which can perform simultaneously or parallel. And for a fact, we know that we will be able to finish our tasks quickly if we can perform tasks in parallel. If we consider computer application, it is also more or less like our house building task. Some part of our application should have done sequentially and there are some part which can be performed simultaneously or parallel. But if we arrange our application code parallel and run it in a single coprocessor, there will not be much gain in performance as in processor level or as in hardware level, we still execute this instruction in sequential order with context switching. But we know that most of the processors in modern PCs or laptops comes with multiple cores. So if we know how to program our applications in parallel, then we will be able to exploit the computation power of these modern hardwares. There are two types of parallelism: task level parallelism and data level parallelism. For example, in our house building tasks, we can assign different workers to perform different tasks at the same time. This type of parallelism is referred to as task level parallelism. And also, we can assign multiple workers to perform same tasks. For example, we can assign multiple people for bricklaying at the same time. We can compare this to multiple threads which are executing same instruction but on different data. This type of parallelism is referred to as data level parallelism. Another thing I intend to clarify before moving on is the difference between parallelism and concurrency. These two terms are most of the time used interchangeably, but they are slightly different in what they represent. As we saw previously, we can run multiple applications simultaneously even we have single core processor. In this case, processor will accommodate this execution with context switching, and for us it is look like a parallel execution. This type of simultaneous execution is referred to as concurrency. This is actually an illusion of parallel execution, but actually in hardware level, we execute instruction sequentially. Parallelism or true parallelism, on the other hand, will happen if we have enough cores in our processor to run each of these processes in different cores. Then all the processes or threads will run in parallel. In this course, however, we will consider both of these terms as equal.